Okay, so before we start, just a couple of reminders. The first midterm will be this Saturday. It will be at 13:30, and I will announce the places where you will be taking the exam. The exam will be in this building, but you will be spread in U1, U2, and U3, the other classrooms in this building. The second announcement is Chapter 6. This week we will be discussing mainly Chapter 6. It is Force and Motion, and it is not gravity. For those of you who prepared prayer reports about gravity, I did accept your prayer reports for the time being, but Chapter 6 in our new book is not gravity. So if you don't want to have problems in the rest of the semester, at least make sure that you check the table of contents of the book of this course, the new book. Now we have been discussing this force and motion also. Last week we discussed about Newton's laws. We had seen three of the Newton's laws. The first one was mainly defining the inertial reference frame, and then we had the second Newton's law, which tells us that the acceleration was proportional to the force and inversely proportional to the acceleration. And the third one, we had this action-reaction pair. So if something is exerting a force on something else, if A is exerting a force on B, then B is also exerting a force on A. So, and they have always they have equal magnitude and opposite in direction. And we had one application of these laws to the motion of an object sliding on an incline. This was let's call this the angle theta. This is the mass of the object. We knew that the forces acting on the object was the weight, and the weight had a magnitude equal to mass times g. Now g is not the acceleration of anything, by the way. G is just a number. G is the number 9.8 meters per second squared. This is just a number with some unit. Of course, it also corresponds to the acceleration of an object if you release it close to the surface of the Earth and no other forces acting on it. So if you just take this object and release it, its acceleration will be equal to g in magnitude. It will be pointing downward. Of course, depending on whether you choose the downward direction as positive or negative, the acceleration might be plus g or minus g, or if you took the acceleration, your axis in some other direction, and it won't even be plus or minus g. You have to write it in a full vectorial form. Now, another force acting on my object was the normal force, and we said that it was perpendicular to the surface. Well, basically, when two surfaces touch each other, there will be like here, there will be forces acting on each one of the objects. The inclined surface will exert a force on our mass. Let's call the mass m. And our mass m will exert a force on the surface. Now this force will have a component parallel to the surface, which we will call friction, and we will be studying friction today. And there is another component which is perpendicular to the surface, and that is what we call the normal force. Now, for simplicity to start with, we just assume that there is no friction. Since there is no horizontal component, the force exerted by the inclined plane on the mass is equal to this normal force, is perpendicular to the surface. Now, this is what we call the free body diagram. This is the free body diagram. In the free body diagram, we don't have the masses. We don't have the inclined plane. We only show the masses that we are studying. In this case, we have a single mass. So we only show that mass, and we only show the forces, that's it. Nothing else. We don't show the decomposition of the forces, we don't show the inclined plane, we don't show the forces acting on the inclined plane, etc. Only the mass that we are studying and the forces acting on our mass. By the way, what are the forces acting on this inclined plane?
Weight, normal, and friction.
Weight of what?
Weight of the object.
Weight of the mass m. Okay, weight of the mass m does not act on the inclined plane. Omega does not act on the surface. This is a common mistake. Omega will not act on the surface. Omega only acts on my mass m. Of course, due to this omega, we have this normal force created. If there is no, at least in this example, if omega was 0, the normal force would have been 0. And the force N is the force that the inclined surface acts on the mass m. So according to Newton's third law, the mass m exerts a force minus N to our inclined plane. Plus, of course, if the inclined plane has its own mass, there will be a mass, there will be a force due to the weight of the inclined plane, etc. But this omega, which is the weight of this mass m, doesn't act on this inclined plane. So whenever you are writing these free body diagram and you are identifying the forces, it is the forces that directly act on your object. Omega does not directly act on the plane. Of course, omega creates this and hence acts indirectly on the inclined plane, but the motion of the object is determined only by the forces directly acting on my mass. Now, any questions on this part? Or any questions in general about the things that we have been doing? Yes. Okay. Perpendicular component of weight, okay. No, the weight does not act on the inclined plane, never. The weight only acts on my object. Of course, it is the perpendicular component of the weight which is responsible for this normal force. But it's the normal force that is acting on my inclined plane.
If you mean
Act? Well, what do you mean by act? Exert some force. The mass, the only force that this mass exerts on the inclined plane is minus N. Nothing else. Other questions? Now that we will study now. In this example, last week's examples, we just ignored the friction. We assumed that the force between these two objects was perpendicular to the surface, and that perpendicular component is what we call the normal force. Now this week we will, in fact, after your question, we will start the friction force. Well, that's how nature works. Why is the acceleration proportional to the force and inversely proportional to the mass? We don't know. We don't have an answer for that. It just seems to be how the nature works.
just an explanation.
It is our observation.
Maybe it is wrong.
Who knows? Well, there are theories, by the way, if you have ever heard of the modified Newton dynamics. They are claiming that if acceleration is very small, then the acceleration is not proportional to the force, or the force is not proportional to the acceleration, but the force is proportional to some function of acceleration. There are some theories. Now, the question is, what are the observational evidences? So at least Newton tells us that the force is, or the acceleration is force divided by the mass. But what are the experiments that he did? What are the limits of this result? And within which limits we tested this result? At least for Newton, we now know that this expression is valid only for velocities slower than the speed of light. If the speed approaches the speed of light, in that case, this expression is not valid. Or it is only valid for gravitational forces that are small. If the gravitational force becomes too big, then the Newton's laws will not hold anymore. We need to modify them. But within the problems that we will study, within the problems that we can observe in our everyday life, the acceleration will be force divided by the mass. I mean, with this information, you can send people to the moon. It's good enough for that. Okay, now let's start with friction. And in fact, let's start with some observations. Okay, this is our book. Now, we had seen in this example, now if you remember the solution, we had found that this mass accelerates in this direction, and the acceleration, the magnitude of acceleration is nothing but g times sine theta. So it's independent of the mass, it's independent of the properties of the object or the inclined plane. Whenever theta is non-zero, there will be an acceleration. There should be an acceleration. But the observation kind of contradicts that. So you see now theta is non-zero, but nevertheless there is no acceleration. Still no acceleration. Still no acceleration. But Newton's law tells me that if there is a force, there is a net force, there should be an acceleration. And if these are the only forces acting on my object, then it's unavoidable that I will have a force parallel to the inclined plane, and it should cause an acceleration. So this basic observation, that although there is an incline, but there is no motion, tells me that there should be one more force in our system, which prevents the motion, which causes the net force to be zero, so that the acceleration of this object is just zero. That is what we call the friction force. Now, let us continue with our observation. Let me say this is the time, this is the necessary friction force. And let us use another example. Let's just take this book. The book is sitting over there. I exert a force with my finger, a time-dependent force. With time, I will increase the magnitude of the force that I apply with time. Now, what I will observe is, for some time it will not move, although I am increasing the force. So there should be, the weight is vertical. Weight cannot balance the force that I'm exerting because I'm exerting a horizontal force. I increase the force that I exert, but it still doesn't move. So there should be another force, horizontal, equal in magnitude to the force that I exert, but in the opposite direction. And it should also be increasing as I increase the force that I exert. So the friction force, the magnitude, will be increasing. If I increase my force linearly in time, the force that I exert linearly in time, the friction force should also increase linearly with time. I increase the force that I exert, increase. At some point it starts to move. This tells me that there is a maximum that this friction force can take. So beyond that maximum, it will not increase. Now, another observation that I have is I exert the constant force. If I exert a constant force, it keeps on accelerating. So those are the observations I have. Until I increase the force, the magnitude of the force to a certain limit, it doesn't accelerate. Once I reach that limit, it starts to accelerate, and the acceleration will be non-zero. So there will be a net force. So it basically tells me that the friction force has the same magnitude as the force that I apply up to a certain limit. After that limit, the friction force somehow gets smaller, because I kept once the object started to move, I kept the force that I exert constant. But if I kept the force that I exerted to be constant, it started accelerating. That means that when I reach this maximum value, although the applied force by my finger is constant, the net force should be non-zero because it's accelerating. So it's accelerating. So the friction force should have dropped somehow. It just drops by a small amount. And again, experimental observation tells us that the friction force doesn't change with time. Although my object is accelerating after that point, when I reach this maximum force, I kept the force that I am exerting constant, so its speed is increasing. Although the speed is increasing, the friction force stays to be constant. Now, up to this point, my object is stationary. After that point, my object is moving. So you see the friction force has kind of different behavior depending on whether the objects are moving or not. So that's why we classify the friction force we divide it into different types of friction. One we call here we call it the the static friction. And here it is the kinetic friction. Now this is just the magnitude. Now what about the direction of friction? Now we will discuss the magnitude of the friction in more detail in a moment. What about the direction?
Opposite direction of the motion.
It's the opposite direction of the motion.
What direction of force?
Opposite direction of the force.
There is some problem my sake. Opposite force, but not. There can be some other forces also. I would say just one force, one push force.
Okay. Well, we have many perpendiculars to a normal force. If this is the normal force, this is perpendicular, that is perpendicular. We have infinitely many perpendicular directions. Well, if the normal force is like that, you cannot have perpendicular and opposite. Opposite is this direction. Opposite of the motion, okay. Okay, let's have this voting. Okay, this will be the question. We can read it. So this is the question. Ignore air friction. I'm just standing here and I start walking in the forward direction, in the plus x direction. So what is the direction of the friction force? This is plus z, plus x, minus x. And we are ignoring air resistance. I'm moving in the plus x. Okay, we will discuss it later on. First, now this question. You can discuss with your friends if you have answered. Okay, let me tell you that the answer is not B. It is not in the plus. Oh, sorry. The answer is not A. The answer, sorry, again. The answer is not B. Now let me ask one more question and then we will discuss both of them together. Okay, ignore about the friction for the time being. So you're starting to work in the plus x direction, again the same situation. You are accelerating in the plus x direction. So what is the force that causes your acceleration in the plus x direction? Newton tells us that if you are accelerating in the plus x direction, there should be a force acting on you in the plus x direction. What is that force? At least the majority of you already told me that the friction force is in the minus x direction, so there should be some other force in the plus x direction. What is that force? It is one of those answers. Okay, so let's discuss this question first. There are basically two answers. No, there are two major answers, let's say A and B. Why A? A is the force that I apply through my legs. Why do you think it is A? So your answer is still A? Okay, you see, the force that will cause you to accelerate is the force that is exerted on you. So the force that you apply through your legs, what is it acting on? You are exerting some force and it is acting on? It is acting on the ground. And it is causing the ground or the earth to accelerate. It doesn't cause you to accelerate. But as you have stated, you are exerting a force on the ground, and hence the third law will have this backward force which will be exerted on you. By the way, what is the force that you are exerting on the ground? It's friction force. Now the friction force has two ways. If you feel a friction force, or in this example, there is a friction force acting by the surface on this object. So by Newton's third law, there is also another force acting on the surface by this object, by the laser. And they are action-reaction pairs. They have opposite directions. And so the friction force, you have to be careful about which friction force you are talking about. And in this example, okay, the force that you exert through your legs, you can only exert a force if there is a friction force between you and the surface. And you are exerting a friction force on Earth, which will cause the Earth to accelerate in this direction. And the Earth is acting through a friction force on you, that's the reaction pair, action-reaction pair, which causes you to accelerate in the forward direction. So the friction force exerted by Earth on you is in the forward direction. Again, your answer is the forward direction, B. The force that is acting on you. Now, any other comments? Now, we will go back to the previous question. Why did you thought that the friction force was in the minus x direction rather than the plus x direction? Any other comments on this one? Okay. It was kind of confusing. So your friend was basically saying that he would determine based on whether the direction of the force that I exert is in this direction or the direction of the force that the Earth exerts is in the opposite direction. Is that basically what you were stating? Okay. You see, the problem is your acceleration or the acceleration of any object is caused only and only by the forces that are acting on you. It has nothing to do with the forces that you exert on something else. Of course, if you are exerting a force on something else, then that something else, due to Newton's third law, should be exerting a force on you, and that force is what's causing you to accelerate, not the force that you exert. So it's always only the forces that are acting on you or that other objects are exerting on you that causes your acceleration. So the force that I exert on Earth has nothing to do with my acceleration. Let me correct it. Has nothing directly to do with my acceleration. Only indirectly. If I exert a force on Earth, then Earth will be exerting a force on me, and due to the force that Earth exerts on me, I will be accelerating. Now, why is it in the plus x direction? Okay, I hope I have convinced you that it is in the plus x direction. We are accelerating in the plus x direction, and the only force acting on me is the frictional force. Of course, there is a weight, but the weight is the vertical direction. Only the frictional force causes me to accelerate horizontally. Why were you confused about the minus x?
I can walk with Newton's and so when you are walking, my feet or left, apply a force and that hurts against the direction.
Okay.
And then because of these forces, I apply first, for example, minus direction, like that.
But that is the force that you are exerting on Earth, right?
Yes. And because of this force, frictions force direction,
Okay. So your answer is A, right?
yes.
Okay. Now, but there are all these people who think that it was in B. What got you confused?
I also answered A, but I think the people who answered B.
Okay, let them speak for themselves. Somebody who thought that the answer was B.
I think about objects moving in one direction, and the friction, it tends to be opposite to that direction. It's just for, I thought the contact object first.
Okay.
If this contact, we say if it's going plus, that has the friction is opposite direction, and it should be minus x. That's what I'm.
Okay. So this is what you usually learn. Even in your book, at some point, it's written more or less like this. The direction of the friction force is opposite to the motion. So if we are moving in the plus x direction, it was natural to expect the friction force to be in the negative direction. But the more correct expression of this one is to the motion of the surfaces. This is the critical difference. Now you see, assume there is no friction. If there is no friction, then I wouldn't be able to walk, but there is nothing that would prevent me to try to walk. And how do you walk? Basically, you lift one leg, press it in the forward, and pull your leg back. And if you pull your leg back, due to the friction, it will not slide. So you just go forward. That's mainly how you walk. But if there is no friction, if you pull your leg backwards, it will just slide backwards. You will not be able to move forward. So the motion of the surface that is creating the friction force is not in the forward direction, it is in the backward direction. And since the surface is trying to move in the backward direction, the friction force is acting in the forward direction, causing my body to accelerate in the forward direction. So remember, this normal force and the friction force are always surface forces. They only depend on the properties and the forces acting on the surface. So the friction force, the direction of the friction force is always tries to prevent the relative motion of the surfaces. When you are walking, the relative motion, if this is you, and you are walking, this is the surface, you are basically pushing your foot backward. So the friction force will try to prevent it. By the way, what is this force? What is exerting this force on our feet that is pushing it backward? The muscles, our legs, basically. So this is the force, let's call it F1. F1 is the force exerting, let's say acting on our feet, acted by our legs. So there are two things. The force should be acting on something, or something is exerting the force on something else, and it is acted by. So if there is a force, then something is acting that force on something else, or that force is exerted by something on something else. So there is F1. F1 is pushing our feet in this direction, in the backward direction. If we are trying to accelerate in the plus x direction, this F1 is pushing our feet backward. So the friction force acting on our leg and on our feet will be pushing it in the forward direction. Okay, is it static or kinetic friction? We are moving in the forward direction. Kinetic, static. You see, always remember, the friction force is a property of the surfaces. It's static. Who thinks it's static? Who thinks it's kinetic? Well, you see, the thing is there a relative motion between these surfaces that's creating the friction force? The friction force is created due to the surface of the earth and the bottom of our feet. Are they in relative motion?
No.
Since they are not in relative motion, the friction force here is the static friction force. Although, of course, my body is moving, but the friction force is only created by the surfaces in contact. It's not created by my body. Now let's look at the magnitudes. So this was our graph of how the friction force changes as I change the force that I exert. So let's say this is the magnitude of the exerted force as a function of time. So up to this point, I kept on increasing it linearly, and after that time it was constant. Now, you see that here, okay, I kept it constant, but I could have as well changed it, increased it. It doesn't really change anything about the friction. So you see, the friction force, the static friction force, doesn't have a constant value. Its magnitude can change, and its magnitude is determined by the requirement that there shouldn't be any motion. But there is a maximum value for that static friction. The magnitude of F static is any value sufficient to prevent the relative motion of surfaces. And there is a maximum value for that. This is always less than or equal to, let's call it, the static friction maximum. And again, experimentally, we know that this maximum value is proportional to the normal force with some coefficient. Okay, one thing you should pay attention to. Okay, the normal force is a vector. The friction force, the static friction force, is a vector. But this is not a vector equation. This is not a relation between two vectors. This is a relation between two numbers, two scalars. These are the magnitudes of these vectors. We know that the friction force and the normal force, as your friend pointed out, they are perpendicular to each other. The normal force is perpendicular to the surface. The friction force is horizontal to the surface. So these two forces are perpendicular. These two vectors, the friction force vector and the normal force vector, they are perpendicular to each other, but their magnitudes turn out, at least the maximum value of the static friction force and the magnitude of the normal force, they turn out to be proportional to each other. Now the kinetic friction force, its magnitude is just constant. As you can see over here, it's just flat. Although I'm changing the force that I exert, or although the object is moving at different speeds at different times because it will be accelerating, the friction force, the kinetic friction force, will not change its magnitude, and its magnitude is always equal to mu k times n. Mu k is the coefficient of kinetic friction and mu s coefficient of static friction. These are just numbers that we have to determine by experiment. Up to now, we don't have any means of calculating these coefficients. We don't know how to calculate them. Now, any questions on these? About the magnitude of the friction and about the direction of the friction? Yes? Yes. True. Because the only thing that determines the direction of the friction is the relative motion of the surfaces creating it. Now, the problem over here that's causing the confusion is up to now we are always, in fact, we will be always discussing with objects that do not change their shape, like the solid blocks. Now, when you have a solid block, all the parts of the object are moving with the same velocity. They will have the same velocity, so if one part of the object is moving in that direction, all the parts will be moving in that direction. And in that case, the friction force will be always opposite to the direction of the motion of the block. In the other example of walking, well, different parts of my body are moving at different speeds. My feet that is touching the ground, my foot that is touching the ground is at rest. It's not moving relative to the ground. Whereas the top part of my body is moving in the plus x direction. That is why we have this confusion about the direction of the friction involved in walking. And when you stop walking, by the way, the friction force is in the minus x direction. Because if you think about your acceleration, if you are walking if you are at rest, you start walking in the plus x direction, then your acceleration is in the plus x direction, so the friction force has to be pushing you in the forward direction. That is the only horizontal force you have. And when you are stopping, your acceleration is in the backward direction. Because initially your velocity was in the forward direction, finally it is zero, so your velocity changed in the backward direction. That is the direction of your acceleration, and that should be the direction of the net force acting on you. So the friction force, which is the only horizontal force acting on you, should be in the backward direction in that case.
How is the friction force related to the normal force?
Experiment. That's our observation. Well, there's no proof. There's no way we can calculate. I mean, if we had a mathematical proof, we could manage to calculate these coefficients. But we are unable to do that. In fact, it's just a simplistic approximation.
Why the kinetic friction force is constant?
Why the kinetic friction coefficient is constant? Well, you see, when you say constant, it is constant within certain ranges. I mean, if I just take this object and let it slide on top of this one, it's almost constant. But you can imagine more complicated objects that when things start sliding, things start get heated up, they can melt, so that even this kinetic coefficient of friction will change. But as I said, this is just a very simplistic picture, very simplistic description of the kinetic friction, which seems to hold quite well in quite general circumstances. Now we will see, for example, the drag force is also a kind of a friction force. And in that case, this doesn't hold. This only holds for friction between two solid surfaces. Observation. Experiment. Yes. Now, when you are studying the direction of friction, trying to determine the direction of friction, always consider the relative motion of the surfaces that are responsible for friction. And that is the only thing that will determine the direction. In this example, the only thing that will determine the direction of the friction forces acting on different objects will be the relative motion of the surface of the earth and the bottom of my feet. On the heel. On the wheel. Oh, so you're... Okay, wheel motion, we will study it when we start studying the rotations. But even in that case, when you have the wheels, the direction of the friction force will be determined only by the relative motion of the surfaces. Even in the case of the wheel, it will be valid.
I think there must be static and kinetic friction.
In this case. Now, between your feet and the surface, no.
So, because at the beginning there is static force, friction, but then my foot moves according to surfaces.
My feet that is touching the surface of the earth is never moving relative to the surface of the earth. I don't get slipping. If my feet are slipping, then the surfaces have some relative motion, and in that case I have kinetic friction. Again, the only thing that will determine the direction and the property of the friction are the surfaces, if creating the responsible for friction. So if the surfaces do not have any relative motion, then the friction force is static. If the surfaces have relative motion, then it will be kinetic. What do you mean?
For example, wood on wood is different than wood on iron.
Sure.
Are the coefficients get subtracted or?
No, I mean, there's no relation. If you put different surfaces on top of each other, they will not be related with other friction coefficients.
You don't subtract coefficients?
No. No. Wood on wood has one friction coefficient. Wood on iron has another friction coefficient. Iron on iron has a different friction coefficient. And as far as we know, there's no relation between these three. Of course, there's one more friction that we will not be discussing. I mean, in your everyday life, if you just slide an object like this metal on wood, it just stops quite fast. The book on wood, it stops quite fast. And, well, there's one more. This is just a ball. In your everyday life experience, you can also do that. If you just roll it, well, it just goes, it will probably go like 50 meters or so. It eventually stops, which tells us that there's some friction involved, But that friction is much smaller than what we are discussing over there, like the static and the kinetic friction. That is called the rolling friction. Now, we will not be discussing it in more detail. But in the next hour, we will be discussing some of the mechanisms that might be causing this friction, and some of them are also involved in rolling friction. Okay, any more questions? Okay, let's give a 10-minute break, and after that we will continue.